Hello everyone. Welcome to today's presentation. I'm excited to share with you our overview of spectroscopic techniques. On this first slide, you can see the title, Spectroscopic Techniques. We'll be exploring various methods used to analyze materials through their interaction with different types of radiation. In the next few slides, we'll cover the main techniques, how they work, and their applications in science and industry. Let's dive in and discover the fascinating world of spectroscopy together. Spectroscopy, or the study of how matter interacts with electromagnetic radiation, is a fascinating field. When light hits a substance, it can be absorbed, emitted, or scattered in different ways. And that's exactly what spectroscopy helps us understand. It allows us to analyze these effects and learn a lot about the material we're studying. For example, it helps us identify what elements or compounds are present in a sample. Think about astronomers using spectroscopy to find out what stars are made of, or chemists analyzing chemicals in a lab. A great example is heating sodium. It gives off a bright yellow light. Spectroscopy tells us that this yellow color comes from sodium atoms. So, by studying the light, we can pinpoint which element is involved. And it's important to remember that each region of the electromagnetic spectrum, from radio waves to gamma rays, provides different kinds of information about substances. This diversity helps us analyze and understand the properties of matter in many different contexts. Let's take a closer look at the spectrometer, which is a fascinating tool. Essentially, it's an instrument used to measure and analyze light coming from a source. What makes it really interesting is its ability to split light into its component colors, creating what's called a spectrum. By doing so, it allows us to measure the wavelengths or the intensities of these colors. This process is crucial because it helps us understand the properties of the light, and by extension, the objects or sources emitting that light. Spectrometers are fundamental in many fields, from astronomy to chemistry, because they reveal details that our eyes alone simply can't see. So, in the context of our presentation, the spectrometer is a key instrument that helps us decode the information carried by light itself. A spectrograph is a type of spectrometer, but what sets it apart is its ability to record the spectrum visually. Instead of just measuring the light, a spectrograph creates a photograph or an image of the spectrum itself. Think of it like taking a picture of the light's signature. While a spectrometer simply measures the different wavelengths, a spectrograph captures a visual record, which can be really useful for analyzing and comparing spectra later on. This distinction is important because it helps us understand how we can visually document celestial or laboratory light sources, making it easier to interpret the data. Overall, it's a powerful tool for turning spectral data into a visual format that can be examined in detail. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the electromagnetic spectrum, starting with radio waves. These have wavelengths longer than 1 meter and carry the lowest energy among these waves. They are primarily used in NMR spectroscopy, which is essential for determining the structure of molecules. Moving to microwaves, which range from about 1 millimeter to 1 meter in wavelength, they have slightly higher energy. These are commonly used in rotational spectroscopy, helping us understand bond lengths and angles within molecules. Next is infrared, or IR, which spans wavelengths from around 700 nanometers to 1 millimeter. IR radiation has medium energy and is used in vibrational spectroscopy, allowing us to identify types of bonds and functional groups in a compound. Then we have visible light, with wavelengths between 400 and 700 nanometers. This range has higher energy and is responsible for the electronic transitions that give compounds their color. Finally, ultraviolet, or UV light, covers wavelengths from about 10 to 400 nanometers. UV radiation has high energy and is used in electronic spectroscopy to explore the energy levels of electrons within molecules. Understanding these different regions of the spectrum is fundamental because each type of radiation interacts with matter in unique ways, enabling us to analyze molecules effectively across various spectroscopy techniques. Now, let's take a closer look at the constant deviation spectrograph, also known as the Hilger wavelength prism spectrometer. This instrument is primarily used to photograph the spectra of various light sources, which helps us analyze their wavelengths more precisely. In this setup, you'll notice that the collimator, labeled as C, and the telescope, labeled as T, are fixed at right angles to each other. This fixed arrangement is crucial because it maintains a consistent geometric relationship, ensuring accurate measurements. The key component here is the constant deviation prism. Marked as P, this is a special type of prism that refracts a light beam at a fixed and consistent angle, no matter what wavelength of light is passing through. This property allows us to accurately determine the wavelength by observing how much the beam deviates. This prism is mounted on a rotatable table, which means we can turn it to different angles. The rotation is controlled by a micrometer screw with a drum attached. Labeled as D, the beauty of this setup is that the drum is calibrated in terms of wavelengths. So when we rotate the prism, it directly shows us the wavelength value of the light we're analyzing. Overall, this design allows us to precisely measure wavelengths by adjusting the prism until the light is properly deviated, with the calibration giving us the exact spectral information we need. It's a clever and effective way to connect the physical movement of the prism to the spectral data we seek. When you rotate the table, you'll notice that spectral lines appear one by one at the crosswires of the telescope. This is a key part of how the spectrometer works, allowing us to observe different wavelengths directly. The wavelength of any specific line can be read straight off from the drum scale, making it a very precise and straightforward process. For photographing spectra, instead of using the eyepiece, we replace it with a camera. This setup allows us to capture the spectral lines for further analysis or documentation. This entire arrangement is known as the Hilger wavelength prism spectrometer. It's a fundamental tool in spectroscopy, helping us analyze light in a very detailed and accurate way. Connecting this to our overall theme, it's all about understanding and measuring the properties of light from different sources, which is essential in fields like astronomy and physics. This slide doesn't contain enough information. That's why we're moving to the next slide. All right, let's talk about setting the instrument properly. First, you'll want to illuminate the slit with light of a known wavelength. This helps us calibrate the setup and ensures accuracy. Next, set the drum to display that specific wavelength value. Think of it as our reference point. Then, carefully place and adjust the prism on the table so that the spectral line appears on the crosswires. It's crucial to clamp the prism tightly in this position to prevent any movement. Now, when we're working with an unknown wavelength, we rotate the drum until the spectral line aligns with the crosswire. This is how we measure the wavelength. Finally, read the value directly from the drum. This process allows us to precisely determine unknown wavelengths by referencing a known standard, tying everything together in our overall exploration of spectral analysis. Now, let's talk about how we record the spectrum in modern spectrometers. You'll notice that photographic plates, which were used in the past, are now rarely employed. Instead, we use a device called a photomultiplier tube, or PMT for short, as our detector, especially for visible and ultraviolet light. The PMT has a light-sensitive surface that, when struck by light, emits electrons through what's known as the photoelectric effect. This is a fundamental process where light energy knocks electrons loose from a material. The tiny electron current produced is then amplified significantly inside the tube. Once amplified, this current is sent to a pen recorder, which measures and records the signal. This setup allows us to detect very faint light signals with high sensitivity. Now, the sensitive part of the PMT, which is crucial for detection, is located at a specific point called point A in our setup. Differently, rays of various frequencies, say nu1 and nu2, are focused onto different points. Specifically at points A and B, this separation based on frequency is essential for analyzing the spectrum accurately. Connecting this back to our overall theme, the use of the PMT and the focusing of different frequencies are vital steps in precisely recording and analyzing spectra, allowing us to gain detailed insights into the light's properties. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's start with the working principle of this setup. First, an exit slit is placed right in front of the detector. This slit is crucial because it limits the width of the beam that actually reaches the photomultiplier tube, or PMT. By doing so, we ensure that only a specific part of the light is detected, which improves the accuracy of our measurements. Next, we have the prism, which is rotated slowly. As it turns, it changes the angle at which light passes through it, effectively altering the frequency of the light that hits the detector. This rotation allows us to scan through a range of frequencies systematically. As the prism rotates, it causes the spectrum to be scanned between 2 points, labeled A and B on the slide. These points represent the boundaries of the frequency range we're interested in. So, by moving the prism gradually, we're effectively sweeping through different frequencies. The outcome of this process is what we call a spectrum in the frequency domain. That means, instead of just knowing the intensity of light at a single point, we see how the detector's output varies across a range of frequencies. This is incredibly useful because it allows us to analyze the spectral content of the light in detail, which ties directly into our overall goal of understanding the properties of the light source and the system. Now, let's talk about how modern spectrometers improve their signals through a technique called computer averaging, or the CAT technique. These spectrometers use electronic amplification to boost the detector signals, making them stronger and easier to analyze. However, this amplification also introduces random unwanted signals, known as noise. Noise can interfere with our ability to clearly see the actual signal we're interested in. That's where the concept of the signal-to-noise ratio, or SN, comes in. It essentially measures how clear or how distinguishable our signal is from this background noise. The higher the SN, the better. For us to reliably recognize and interpret a signal, we generally need a minimum SN of about 3 or 4. By using the CAT technique, we can average multiple scans to improve this ratio, making our signals much clearer and more reliable. This is especially important as we aim for precise, accurate spectroscopic data, connecting this to our overall goal of obtaining high-quality spectral information. Let's talk about the computer averaging technique, or CAT. Essentially, it's a method used to make weak signals more visible within a spectrum. The computer records the spectrum step by step, capturing small segments. Imagine it recording 2,000 tiny points and noting their brightness or intensity. Then, it repeats this process many times. Each time, the new data is added to the previous data, effectively stacking the information. This process is crucial because by averaging out the repeated recordings, the real signals, those consistent features, become clearer while the random noise diminishes. So, in simple terms, CAT involves recording multiple times and averaging the results. This way, the true signal remains, but the noise gets reduced, making weak signals much easier to analyze and interpret. It's a powerful technique that enhances our ability to detect subtle features in the spectrum. All right, let's talk about how signals and noise behave when we analyze them repeatedly. The key idea here is that the real signal, the true information we're after, adds up each time we observe it. So, with each new measurement, the signal gets stronger and stronger. On the other hand, noise, those random unwanted signals, don't add up in the same way. Since noise is random, sometimes it adds positively, sometimes negatively, so it only increases slowly, specifically by the square root of the number of observations. Now imagine we do this process n times. The signal becomes n times bigger, which is a linear increase. But the noise only increases by the square root of n, which is a much slower growth. This means that, over time, the signal stands out more clearly against the noise, improving our signal-to-noise ratio. For example, if we record the spectrum 4 times, the signal gets 4 times stronger, but the noise only increases by 2 times, since the square root of 4 is 2. As a result, our clarity improves, specifically, it doubles. So by repeating measurements, we make the signal clearer and easier to analyze, which is fundamental in extracting accurate information from noisy data. Ultraviolet spectroscopy, or UV spectroscopy, covers a range of wavelengths from about 300 nanometers down to 10 nanometers. This part of the spectrum is produced using various sources such as mercury vapor lamps, electric arcs, or hydrogen discharge tubes that are made of quartz. These sources emit UV radiation that we can then analyze. To obtain UV spectra, we typically use optical components like prisms, which are made from materials that don't absorb UV light or diffraction gratings. When working with wavelengths below 110 nanometers, reflection gratings are especially useful because they handle these shorter wavelengths more effectively. Recording UV spectra involves photographic techniques. Special plates like Ilford Q plates are used for capturing the spectral data. When we're trying to identify unknown wavelengths, we compare the recorded spectra with standard reference spectra, which helps us determine their exact positions and characteristics. This method is a vital tool in our analytical arsenal, especially for identifying substances and understanding molecular structures through their UV absorption patterns. It connects directly to our broader goal of characterizing materials based on their interaction with ultraviolet light. It looks like the slide content is a link to a YouTube video, but I don't have the ability to access external links. Could you please provide the text or main points from slide 18? That way, I can craft a detailed and natural narration script for you. Let's take a closer look at the quartz spectrograph used for the near ultraviolet region. As you can see, glass tends to absorb ultraviolet rays, which is why we use quartz lenses and prisms in this setup. Quartz is transparent in the 200 to 400 nanometer range, making it ideal for detecting UV light. This spectrograph includes several key components: a collimator, a Cornu prism, and a camera with a photographic plate. The photographic plate is inclined at about 20 degrees to optimize the focus and exposure. Here's how it works. Light from the slit first passes through the collimator, which makes the light rays parallel. Then, the light enters the Cornu prism, which is made of two quartz prisms with a 30-degree angle but of opposite-handedness, enabling precise refraction of the UV rays. After refraction, the light is focused by the camera lens onto the photographic plate. This setup captures a photograph of the UV spectrum, which we can later analyze. Finally, to measure the wavelengths, we compare the photographic spectrum against a known standard using a comparator. This method allows us to accurately determine the spectral lines in the near UV region, which is crucial for various scientific applications. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about infrared spectroscopy. The infrared, or IR, region of the electromagnetic spectrum is actually beyond the red end of what we see. It spans from about 720 nanometers all the way to 400 microns, covering a wide range of wavelengths. When it comes to generating IR light, common sources include the Nernst glower, which is essentially a heated filament made from rare earth oxides, and the globar, which is a heated silicon carbide rod. These sources are critical because they provide the IR radiation needed for analysis. Now, unlike visible light instruments, infrared spectrographs use mirrors instead of lenses for focusing and dispersing the light. This is primarily because mirrors are more effective at handling IR wavelengths. And because no single material can transmit the entire IR spectrum, different prism materials are used depending on the specific wavelength range we're working with. This ensures we can accurately focus and disperse IR radiation across the spectrum. Connecting this to the bigger picture, understanding how IR light is generated and manipulated allows us to analyze molecular vibrations and identify substances based on their unique IR absorption patterns. It's a powerful technique that, when combined with the right equipment, unlocks a lot of chemical information. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the Wadsworth prism mirror spectrograph. In this setup, light from a source is first focused onto a narrow slit. Then, mirrors work to make the incoming light parallel, which is essential for accurate dispersion. Next, the light passes through a combination of prisms and mirrors that disperse the light into its component wavelengths. The dispersed light is then focused onto an exit slit, which acts as a sort of gate for specific wavelengths. A thermopile detector measures the intensity of different wavelengths as the prism rotates, allowing us to analyze the spectrum. All these components are housed inside a protective box to prevent stray light from interfering with the measurements. And although this setup is optimized for visible light, once properly focused, it can work well across a range of wavelengths. This design is a great example of how precise optical engineering allows us to analyze light in detail, which is fundamental to many spectroscopic applications. Now let's walk through how the Wadsworth prism mirror spectrograph works. First, light enters through slit S1, and it's made parallel by the concave mirror M2. This step is crucial because having a parallel beam ensures accurate dispersion of the light later on. Next, this parallel beam passes through the prism mirror combination. The prism is responsible for dispersing the light into its component wavelengths, creating the spectrum we're interested in observing. After the light emerges from the prism, it hits another concave mirror, M4, which focuses the dispersed light onto the exit slit, S2. This focusing is important because it allows us to select specific wavelengths for detection. At S2, we have a linear thermopile, which is used to detect the radiation. It converts the incoming light into an electrical signal, giving us quantitative data about the intensity of each wavelength. To scan through different wavelengths, the prism can be rotated. As it rotates, different spectral lines pass through the exit slit one after another, allowing us to analyze the spectrum in detail. Finally, all the mirrors and the prism are enclosed in a box. This enclosure prevents stray light from interfering with the measurements, ensuring our observations are as accurate and clean as possible. This entire setup, from the collimation to the detection, illustrates how the Wadsworth spectrograph enables precise spectral analysis, a key tool in many fields of optical research. Now let's take a closer look at the grating spectrograph for infrared radiation. First, infrared rays are focused onto a small hole located at the center of a plain metallic mirror, which we'll call M1. This tiny opening is crucial because it helps direct the incoming infrared radiation efficiently. This hole is strategically placed at the focus of a concave mirror, designated C1M1, which helps concentrate the rays onto the hole. Once the light passes through this opening, it reflects and then encounters a diffraction grating. Labeled G, this grating is essential because it splits the light into its component wavelengths, much like a prism, but with a different mechanism. After dispersion, the light is directed by two additional concave mirrors, CM2 and CM3, along with a plane mirror, guiding the separated wavelengths toward an exit slit. Called M2, the purpose of this setup is to precisely select the specific wavelength we're interested in analyzing. Finally, the light that passes through the exit slit falls onto a thermopile, T, which detects the infrared radiation. The key here is that the grating isn't fixed, it's rotated using a graduated drum. This rotation allows us to bring different wavelengths to the exit slit one at a time. By measuring the angle of this rotation, we can accurately determine the wavelength of each radiation. This process enables us to analyze the infrared spectrum in detail, which ties back to our overall theme of understanding infrared properties through spectroscopic techniques. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about absorption spectroscopy. The process starts with a light source that emits radiation across a broad range of wavelengths. When this light passes through the sample we're studying, some of it gets absorbed depending on the material's properties. The key here is that the transmitted light, the light that makes it through the sample, is then analyzed spectrally. By examining how much light at each wavelength is absorbed, we can determine specific characteristics of the sample. This method allows us to identify and quantify different substances based on their unique absorption patterns, which ties back to our overall goal of understanding material composition through light interactions. This slide doesn't contain enough information. That's why we're moving to the next slide. let's take a closer look at the block diagram of an absorption spectrometer. This diagram illustrates how the instrument works across the infrared, visible, and ultraviolet regions. The process begins with a white light source, which emits a broad spectrum of radiation. This radiation is guided through a lens or similar device to focus it onto the sample. Once the radiation interacts with the sample, some wavelengths are absorbed depending on the sample's properties. The transmitted radiation then passes through an analyzer, which in this case is a prism. The analyzer's role is crucial because it selects the specific frequency or wavelength of light that reaches the detector at any given moment. This selective process allows us to analyze how much light is absorbed at each wavelength, which is key to understanding the sample's characteristics. The detector captures the transmitted light and converts it into an electrical signal. This signal is then sent to a recorder, which is synchronized with the analyzer. As the analyzer varies the wavelength, the recorder plots a trace of absorbance versus frequency. This trace ultimately provides us with valuable information about the sample's absorption spectrum, helping us identify and quantify various substances. This entire setup exemplifies the core concept of absorption spectroscopy, using controlled light sources, wavelength selection, and detection to analyze material properties. This slide doesn't contain enough information. That's why we're moving to the next slide.